At the end of my last lecture, I briefly mentioned the mathematical background that we must go through in order to ultimately understand how Galileo experimentally overturned the two ancient Greek notions regarding motion near the surface of the earth. He overturned those notions experimentally. We have to go through, however, some mathematical background first in order to understand exactly what it was that Galileo did. As I go through this mathematical background, we are doing so entirely by using modern notation. Specifically, we have to describe vectors. Okay, so first of all, right off the bat, what is a vector? Well, a vector quantity is any quantity that has two things associated with it. A size, typically referred to as a magnitude, and a direction. Any quantity, size, once again that's referred to as magnitude, and direction. Probably the simplest physical example of a vector quantity is position. So for example, let's say that you are going to describe the position of me in this room. You were saying going to describe my position to somebody else. If you were to do so, you would basically have to state two things. So first of all, let's picture this room here as a reference frame, as a coordinate system. And then let's say at the door, which is over there on my right-hand side, we can think of the door as the origin, a point of reference. So then therefore my position relative to the door, if you were sitting here in my classroom, could be described in the following way. If you were sitting in this room and facing me, you would see that I would be standing to the right-hand side of the door. And then I would be some distance from the door, right now maybe about 10 feet or so from the door. So then therefore you would say that my position is 10 feet to the right-hand side of the door. So you described a vector quantity, you described the magnitude, 10 feet, and a direction to the right-hand side of the door. Okay, now that's a little bit different from what is referred to as a scalar quantity. A scalar quantity is any quantity that only has a size or a magnitude associated with it, no direction. So scalar is any quantity with size only, in other words, magnitude only. Ordinary numbers, for example. Numbers that you've been working with in mathematics since day one of primary school are scalar quantities. They are quantities that only have a magnitude associated with them, but no direction. So nobody told you this at the time. When you first started to learn mathematics in primary school, you were actually beginning by learning what is called scalar mathematics. We're now going to broaden that to include vectors in just a few minutes. Before I do, however, a nice, easy physical example of a scalar quantity would be temperature. So for example, you would say that the temperature in this room is 70 degrees Fahrenheit. You would not say, however, that it's 70 degrees Fahrenheit to the north. In other words, there's no direction associated with temperature. There's only a magnitude associated with it. Therefore, temperature is a scalar quantity. Okay, now getting back to vectors themselves. There is a specific way in which we denote a vector. In other words, there is a notation that is used. Okay, first of all, we always draw out a vector graphically as an arrow, like so. And let me go ahead and give this vector a name. I'm going to refer to this variable here as A. Okay, now to denote it as a vector quantity on the board, you're going to always see me write the vector symbol above. The vector symbol itself is the arrow that is written here above the letter A. However, in textbooks, including your own, you're always going to see vectors denoted in bold type. So you'll see bold type for the letter A instead of having the vector symbol above. But when I draw it here in this room on the board, you're always going to see me draw the vector symbol. But in texts, vectors are in bold type. Okay, and then there are two things associated with this vector. First of all is its magnitude, basically the length of the arrow that I just drew. In order to describe the magnitude, we always just draw the letter A all by itself without the vector symbol. However, in textbooks, you're always going to see the magnitude written in normal type. So in texts, the magnitude is in normal type. Okay, and then there is a direction associated with this vector. We usually denote the direction as an angle of some sort. So let's say, for example, that this right here represents the positive x-axis, and then with respect to the positive x-axis, the vector here, A, forms an angle. That angle here I'll just refer to here as theta. So what I'm depicting here are two things associated with the vector quantity A, that is its magnitude and direction. And now at this point, we start to do basic mathematical operations involving vectors. The simplest mathematical operation to look at is vector addition. That is what happens when you add two vectors together to then result in a third. We'll take a look at a one-dimensional case, and then a little bit later on, we'll also take a look at a two-dimensional case. Okay, so one-dimensional vector addition. I do lots of examples in class. As I do examples in class, the way that I do so is I project the examples up onto my screen, which is out of shot with the camera on my phone. What I usually have my students do is they then copy down the example into their notes. Once I've given them a moment to do so, I then lead the students through the solution here on the board. I'm going to do the same with you. So at this point, what I want you to do is pause this lecture, and then in the folder, you are to access the handout or the document called Lecture Examples. Go ahead and copy down the first of those examples into your notes. Okay, now that you've copied down that example, let me go ahead and read it to you. So the beginning of the example is as follows. A student is initially at rest. Then he walks 5 meters to his right and then 10 meters to the left. In part A of the problem, we're asked to calculate the student's final position. Okay, so what we have here are two vector quantities. We have the first position vector, which is 5 meters to the right, and then the second, which is 10 meters to the left. Let me call the first vector, vector A. So vector A is equal to 5 meters to the right. Now notice that I depict here two things when describing this vector. I depict its magnitude and direction to the right-hand side. Let's just simply think of right and left horizontally as a number line. And anything to the right-hand side we'll say is the positive direction, and anything to the left-hand side is the negative direction. So then therefore writing the phrase to the right becomes somewhat redundant. Instead what we'll do is we'll write this vector as positive 5 meters. And then we have the second vector, vector B, which is 10 meters to the left. Once again, however, writing the phrase to the left is somewhat redundant. Instead, we'll think of the left-hand side of the number line as the negative direction. Therefore, we'll write the vector B here as negative 10 meters. Okay, and now what we're going to do is we're going to add the two vectors together to obtain the student's final position. When we add the vectors together, this then results in a third vector. This third vector, the sum of the two, is sometimes referred to as the resultant. Let's call that vector C. Now, of course, mathematically, this is trivial. There's nothing to it. If you add A and B together, the student ends up 5 meters to the left-hand side. But vectors are graphical quantities, and we can also add them together graphically. I'm going to do so on a number line by using a specific method. This method is called the tail-to-tip method of vector addition. Okay, so let me begin by just drawing by hand. That's perfectly fine for this one-dimensional case, a number line. So here's a number line like so that's representing position in terms of meters. And then let's say, for example, that I have here 5, 10 meters to the right-hand side, and then 5, 10 meters like so to the left-hand side. We'll assume that the student starts at the origin, and then the student walks 5 meters to the right. That's the vector A. So on this number line here, I'm going to go ahead and draw the vector A then, like so. And then what I have to do is add to it graphically the vector B. What we do is we take the tail of vector B and we place it at the tip of vector A. That then starts at this point right here. And then therefore, I'll draw below the number line such that we can see it. Right here is the vector B. So notice that I'm placing the tail here of B at the tip of A. And then the resultant, the vector C, is always drawn from where we initially begin, here at the origin, to where the student ends up. So using a third color, for example, like so, right here is the vector C. Here's how you pantomime this method of the tail to tip method of vector addition. What you do is we start at the origin, and then we have here our first vector A, and then we add to that the vector B like so, and then therefore the resultant goes from the origin here to where we end up. So A plus B is equal to C, like so. Okay, now take a brief moment to copy down part B of the problem if you haven't already done so. I have to show that here on my screen. So in part B of the problem, it says, what would the student's final position be if he had walked to the left-hand side first? So what we're doing here in part B, very simply, is we're just reversing the order of addition. If you think back to ordinary scalar mathematics, when you reverse the order of addition, that's referred to as the commutative property. We're looking at that briefly here in part B. Okay, so now we're going to have C is equal to B plus A. Numerically, of course, it's the exact same thing as it was before. It was negative 10 meters plus positive 5 meters for negative 5 meters, like so. Ultimately, however, we can show this graphically by once again using the tail to tip method of vector addition. That's drawn like so. So here's my number line once again, representing position in meters. So we have 5, 10 to the right, 5, 10 to the left. But now we begin with the vector B. So the vector B of negative 10 meters is drawn like so from the origin, and then 10 meters to the left-hand side. And now what I have to do is take the tail of A and place that at the tip of B. Now recall that A points to the right-hand side like so, with a magnitude of 5 meters. So right here what I'm doing is I'm taking the tail of A and placing it right here at the tip of B. And then the resultant, C, is drawn exactly the same way as it was before in part A of the problem. That is from the origin where we start to right here, 5 meters to the left-hand side. If you pantomime this by using the tail to tip method, what we have here is B plus A is equal to C, like so. And of course, we get the exact same answer as we did earlier in part A of the problem. Notice that it's perfectly fine to move the vectors around in space. Compare, for example, vector B on the diagram above to where it is here on the diagram below. You can move vectors around in space as long as you maintain two things about them. Number one, the magnitude, and then secondly, the direction. Notice that the magnitude and direction of the vector B, for example, is exactly the same on both diagrams. Okay, now it's nearly not necessary for me to go through a specific example of this, but it should be, at this point, no surprise that vector addition also obeys the associative property. Okay, I can easily illustrate the associative property by adding three vectors together. For example, let's say that we do the following. Like so. So here what we do in parentheses first, recall your order of operations. We add together A and B, take the resultant of that, and then add it to a third vector, C. This is ultimately the same thing if instead we did the following. Once again, recall your order of operations. Here on the right-hand side of the expression, what we do is we get the resultant of B and C first, and then add that to the vector A. If we did that, we would get exactly the same thing as what we here have originally on the left-hand side of the expression. That's the associative property. Okay, moving on from there, however, still retaining one-dimensional situations, let's now see what happens if you take a vector and you multiply it by a scalar. Not multiplying it by another vector, that's something that we'll get to much later on, but instead taking a vector and multiplying it by a scalar. The easiest way to illustrate this very simply is to just once again do another example. So at this point, pause the lecture and go ahead and copy down now the second example into your notes. Okay, here's what we're given in that example. Okay, we're given a vector A as positive 5 meters. Notice, by the way, in the Word document that the letter A there is in bold type to indicate that it's a vector quantity. And I'll just graphically represent the vector A like so. I can do so safely here without a number line because I'm just drawing this out rough. That's fine. Okay, now very simply in part A of the problem, all that we do is we just multiply it by 5. So what we do, it ends up being positive 25 meters. So this new vector is 5 times larger than the previous vector, but it still points to the right-hand side. So roughly looks to say something like this. And now in part B of the problem, however, what we'll do in this case is multiply by a negative number. So when we multiply by a negative number here, we first of all just end up with negative 15 meters. We not only change the magnitude of the vector, but we also change its direction. We change its direction by 180 degrees. So then therefore the vector negative 3a looks roughly like so. So multiplying a vector by a scalar is easy, it's trivial. However, when you do multiply by a negative number, you do have to take care to reverse the direction by 180 degrees. So we opened here with 2 simple situations involving mathematical operations of vectors in one dimension. In the next part of today's lecture, in the next part, or the next video, I guess I should say, what I'll now take you through is 2-dimensional vector addition. I'll do that in the next video.